Hi, everyone, and thank you so much for listening to this exciting interview today. So I'm Kaylee. I run Circular Digest, a monthly newsletter to support individuals, organizations, financial institutions who really want to accelerate the transition to a circular economy. So every month I release creative insights, actionable recommendations, and expert deep dives digging into the strategy, policy, finance, innovation aspects of the circular economy. So I'm delighted today to have with me Fabio Lamberti, works for AquaPak Polymers as an R&D scientist, to talk about chemical recycling. Now, chemical recycling is, I would say, a fairly controversial topic. Some people believe it is the way that we need to use to get enough recycled content at the quality we want to meet our recycled targets. Other people think maybe it's a bit of almost a cop-out, if you will, to use it as a way that we can continue generating plastics without reducing and reusing, and our strategies further up the waste hierarchy. So I have Fabio here with me today, and we're going to dig deep into the topic of chemical recycling. So Fabio, thanks so much for joining. Could you just introduce yourself, please?
Yeah, so thanks for having me. My name's Fabio. I work for AquaPak as a development chemist. So I'm responsible for creating new formulations for different application areas, such as blown film, non-wovens, extrusion coatings, etc. My background, I have a master's in chemistry and a PhD in chemical engineering, and my PhD focused on the chemical recycling of PLA, and it was one specific method of that. Thanks for having me. Let's get stuck in.
Great, let's do it. So first, I think the first question is, what is chemical recycling? It's such a big topic. So what is it? What are the different types? And could you explain it in layman's terms?
Yeah. So it's a bit difficult to explain without the context. So I'm just going to provide a bit of the context to, what a polymer is, because otherwise I can't really explain it. So if we imagine a polymer as a long chain of repeating units, chemical recycling allows you to slice up that polymer chain into smaller units. So usually we have monomers that we polymerize, and then you have a polymer. Chemical recycling will allow you to take the polymer and go back to the initial raw material, so back to the monomer. So that's very much a layman's terms. In terms of the different types, there's so many different types of chemical recycling. Whenever you say it in the industry, people mostly think about pyrolysis, which is basically you're taking mixed plastic waste and you're heating up to a very high temperature, about 400 to 700 degrees. You might be using catalysts, you might not. And this is done in the absence of oxygen. And what will happen is you'll cleave those polymer chains into smaller hydrocarbons. So, you'll have a range of hydrocarbons from, maybe a 3 or 4 chain length up to 12. You have a range, and then your product, you end up getting oils, waxes, chars, and then you have to send that to like an oil refinery to turn that into something a bit more useful. So a reason when you say chemical recycling, it tends to get a bad rep is because people assume it's only this. And even then, pyrolysis has come a long way in the past decade or so. But it does have some issues. It's high energy intensive. Your product selectivity isn't that great. There's a lot of purification steps as well that happens downstream. So it's not necessarily the ideal solution, but it should be done in tandem with mechanical recycling, for example. Another type of chemical recycling technique, which is similar, is called gasification, which is very similar to pyrolysis, but it's at an even higher temperature. So it's about 800 to 1,000 plus degrees. And because it's a higher temperature, you're cleaving those polymer chains into smaller units. So you're going down to, you know, 2 or less units, and you produce something called a syngas, and you can then use that to generate electricity or to fuel, you know, some machinery. So they're sort of good, but I think where I think people need to sort of appreciate there's another technique, which is depolymerization. And even in this, it's sort of like an umbrella term. There's many different types of techniques you can do, but they all sort of work around the same concept, that you're adding a solvent, you're adding a attacking nucleophile, and you're adding heat, and it's cleaving those polymer chains at those specific units again. But it's probably better than the other two methods. So if I go into a bit more detail here, you know, if I take a PET plastic bottle, for example, if I was to chemically recycle that by solvolysis, so I could use alcoholysis, glucolysis, and other types where I'm using a solvent, I'm using heat, it will cleave those liable bonds in the chain, and then you end up with a monomer that you can repolymerize back into your you can repolymerize back into a polymer. But so if I take a PET plastic bottle, recycle it by this method, I can end up with pellets that I can blow into another bottle, which will be identical to the original. So this is where chemical recycling really has big potential, because everyone wants to talk about circular economy, but without chemical recycling, you can never be circular, right? Mechanical recycling has flaws, and it's linear in a way, whereas introducing chemical recycling helps fill those gaps. So that's just a brief summary, but by no means have I covered all the techniques. There's so many different ones out there, and again, each technique will have advantages and disadvantages depending on the polymer, right? So the polyolefins, so you have polypropylene and polyethylene, those are the two most common polymers out there. They make up, I think, about half of the annual production, which is, I think now it's like 400 million tons a year. So half of that is just these two polymers, and those two you can't actually recycle by solvolysis methods, because when you look at the chemical structure, there's no sort of weak bonds. It's all carbon-carbon bonds. So your only options are pyrolysis or gasification. But again, this should be done in tandem with mechanical recycling. So yeah, that's just a brief summary of everything.
Great, thank you so much. Yeah, it's a very complex field for sure. So we've briefly touched on this, but my next question is, how does chemical recycling compare to traditional mechanical recycling in terms of energy consumption, environmental impact, output, and recyclate quality as well?
Mm-hmm. So mechanical recycling, it is a fantastic thing, and you should use both together. So mechanical recycling wins in terms of energy input, environmental impacts, because you need lower temperatures, right? And you don't necessarily need these solvents or other like nasty chemicals. So if I go back to the example of a PET bottle, if I was to mechanically recycle that, I would grind up the post-consumer bottles and feed it through a extruder. But the problem is, if you was to use 100% of recyclate material, the final product would be rubbish. Because during the mechanical process, you get a lot of mechanical stress, thermo stress as well, and that actually degrades the polymer chains, right, and causes side reactions, and there's contamination as well, and that results in a product that's inferior. It can't be used in the same application. So where I gave the example of chemically recycling a PET bottle, you end up with a product that is like for like with the original. Mm-hmm. If I was to mechanically recycle that, it's not like for like. You might not even be able to make a bottle, because it won't have the actual properties. You'll have to downgrade it and use it in a different application. So when people mechanically recycle PET, they might end up making like PT fibers, polyester fibers, because it's a downgraded application. It's a less demanding application. And one way they sort of overcome that when they mechanically recycle is they use a virgin input, meaning a raw material that hasn't been used before. And by doing this, they can combat some of that degradation. So a PET bottle, if you was to mechanically recycle that, people tend to use 30% recyclate to 70% virgin material. And you would end up with a plastic bottle at the end that is sort of like for like with the original, still some diminished properties, but it's good enough to meet the requirement. So in terms of environmental impacts, mechanical recycling wins, but as I said before, it will never be circular because it has this linear input. I'm having to input virgin material, and this is where chemical recycling helps fill in the gaps, right? Because over time, as you continue to do repeat cycles of mechanical recycling, the product properties become worse and worse, and it gets to the point that you can't even blend it with virgin material. It's no good. So what do? So the only option then is to landfill or to incinerate. And both of those have issues as well. So this is where chemical recycling comes in as the alternative. So although it does have a higher energy requirement, it helps fill the gaps. It allows you to deal with degraded materials. It can handle mixed waste as well. So with mechanical recycling, your input has to be clean, has to be one type of polymer, right? Whereas chemical recycling is a bit more robust. So it might lose on the energy impact, but then when you look at, end of life, it's still better than incineration or landfill. So both technologies sort of work together. I'm not saying one's better than the other, but yeah.
Interesting. Yeah, I was reading an article and they were saying a pro of chemical recycling is almost just from consumer perception. So you mentioned it's often 70% virgin, 30% recycled.
Mm-hmm.
And so obviously there's that structural element you were talking about, but I think also to do with the color as well. So the color gets a bit more cloudy, a bit more opaque, and consumers just don't really want to buy a water bottle if the bottle is not super clear, because you get the perception that it's dirty. So that was quite interesting, that there's also all this consumer perception and consumer behavior to think about as well. And even though, you and I are very environmentally minded, but the average person, that may be a key indicator as why they wouldn't buy something like that.
Yeah. I mean, it's interesting because when you talk about, the average person, they might buy, a Coke bottle off the shelf that says made of 100% recycled material, and that's greenwashing. That's a lie, because when they mechanically recycled it, they had this virgin input. They don't say on the bottle, this is made of, 20%, 30% recyclate, and the rest is, they don't specify that. Consumers don't really know the difference. Consumers don't usually know different types of plastic. They just say plastic, and it's all one type. And I don't think the solution, while educating consumers helps, I think the real solution happens downstream, happens with legislation and creating the infrastructure to actually handle waste materials, separate waste materials and put it into the right streams. So yeah, it is a problem, but I think we are moving in the right direction.
Amazing, great. So you mentioned the different inputs that need to be mixed together to create these recycled materials. So mass balance is something that is often talked about as an accounting, if I may be wrong here, but like an accounting way of understanding how much recycled content is used. So could you explain what is mass balance and how is it used in chemical recycling?
Yeah, so you're exactly right. In chemical recycling, it is, and even in mechanical recycling, mass balance is a accounting framework. It's a way of tracking what percentage of recycled material you've put in. So let's say I have a big facility and I'm mechanically recycling, right? I'm putting, again, I'm just going to pick 30% recycled material to 70% virgin. Once it's in the machinery, you can't exactly separate the molecules to be like, oh, this is a recyclate molecule, this is a virgin molecule. It doesn't really work like that. So mass balance is a way of saying, if my input is this percentage recycled, my output is that same percentage recycled. So it is a way of keeping track. But yeah, mass balance means different things in different fields. So, but in this context, it means it is a tracking.
Okay, great. I've heard of mass balance being sometimes a bit controversial. Is it a controversial method of accounting?
I don't think so. I don't think so. I think recycling in general is controversial. So, you know, it might come from that. But mass balance definitely works.
Okay.
And it would be more more obvious to the consumer. Like, let's say they're buying that bottle off the shelf and it says it has the mass balance and it says, oh, it's this amount recycled material. It does educate people a bit better.
Yeah, definitely. And then we just need the companies to not be greenwashing and saying it's 100% recycled if not. Thank you. So we've already touched on this, and you've already mentioned it quite a few times, that you view mechanical recycling as a complementary process to chemical recycling. So both is needed, and I guess for different products, polymers, applications, to transition to a circular economy where we keep materials and products in use for as long as possible, right? So I guess my next question is, we've talked about the benefits and advantages of chemical recycling, but I want to touch a bit more on maybe the limitations or challenges that chemical recycling has had. So you've mentioned previously it does have high energy consumption and you need to use solvents, which I guess if not managed properly in a facility potentially could cause some pollution. Are there any other kind of limitations or challenges that the audience should be aware of?
Yeah. So there's the energy requirement, which is really a cost issue. It does require quite a large amount of capex to get it off the ground. And then there's purification is a big issue. So I mentioned with pyrolysis, you ended up with a product that you have oils, waxes, and you have to purify it. And that just brings additional costs, additional energy requirements to the overall process. But it's still better than landfill or incineration. And if done correctly, you can mitigate it. So, you know, if you pick a solvolysis technique, you mentioned, you know, what if the solvents leak, leave the system? If you've done it correctly, no solvent will leave. You'll capture everything and reuse everything, right? So it's quite complex and does require a lot of thoughtful thinking before, like, you can't just, oh, I'm going to open up a recycling plant overnight. It takes a long time. There's a lot of people that has to be involved. There's supply chain issues as well. But I think the main takeaway for the consumers, just chemical recycling has a very high energy requirement, and with that comes the cost. But that's still better than what we're currently doing, that we're just polluting the environment.
Interesting. And you mentioned it is very costly to set up these facilities. In your opinion, is there any policy that could support the scaling up of chemical recycling?
Yeah, definitely. So I've heard of before with pyrolysis that there were some subsidies from the government. So per barrel of oil, the government might pay you X amount of money. So they could definitely put out incentives out there to, you know, help these chemical plants get over the line. But really, I think the main driver would be to put out legislation that punishes pollution, because then you're forcing these businesses to think, oh, now we have to deal with this, right? And the only way they can deal with it is mechanically or chemically. So I think that's the approach.
Okay, great. And I know there's a lot of extended producer responsibility that's coming into force all over the world, really, making sure that companies, producers, are responsible for the end of life management of the products they place on the market. So I imagine extended producer responsibility can be a really key driver in getting these companies to actually invest in the end of life management solutions to what they're producing. So I think if we can talk a bit more about the role you see chemical recycling playing. So you already mentioned you see it as a complementary process, but maybe we could dig a bit deeper into that. So in the broader strategy of reducing plastic waste and promoting the circular economy, where do you really see chemical recycling fitting in with all the other stuff we do? So of course, mechanical recycling, but also reduction, reuse, and things further up the waste hierarchy. Yeah, kind of how do you see those interactions playing?
So I think the primary focus would first be to reduce plastic where you can, and redesign the materials to recycle easier. So, a mono material rather than a 9-layered material, right? And that actually eases the burden on all the recycling systems, mechanical and chemical. So I would say the main strategy should be, reduction and redesign. And when you can't reuse, where you can't reuse a product, you should then mechanical recycle it. When mechanical recycling then fails, that's when you introduce chemical recycling. It's sort of the last resort, right? Currently, our last resort is landfill and incineration, and I think that should sort of be replaced, and we should put chemical recycling there. Even with chemical recycling, you might have a small percentage coming off that you can't do anything with. So there'll still be the use for incineration, there'll still be the need for it, but currently we're using it as a crutch. Like a lot of our waste just go straight to incineration. And when you think about it, a lot of energy is put into the polymerization process to make these polymer chains. And when we incinerate it, we're just completely destroying that. So there's a lot of energy loss. Whereas if you chemically recycle it at that stage, you're recovering that energy, right? And then when you look at the overall process, it is financially better. When you look at life cycle assessments, chemical recycling comes out above incineration. So I don't think it's the silver bullet. And when we started this discussion, you mentioned that chemical recycling gets some hate, and some people use it as an excuse to say, oh, we'll just carry on doing what we're doing, we'll just chemical recycle it. No, that's not what we should be doing. We have to reduce, we have to redesign, we have to mechanical recycle. And only then, when you have a degraded product what do I do with it? That's when you chemically recycle. So they're all meant to work together.
Yeah, and I think to transition to a circular economy, all these levers we need to pull for every application. 100%. We produce so much and we consume so much, and it would be very unrealistic to think one method will fix all our problems.
Yeah, I just want to caveat as well. When I say reduce plastic, I'm not talking about replace plastic with paper or glass. You see this a lot, that there's a lot of I don't want to say plastophobia, but plastics do tend to get villainized because we're visual creatures. We see the pollution, we see the problem, and we think, oh, plastic is a problem. But the reality is, since the commercialization of plastics, we've improved the quality of life globally. There's a reason it's used in every single sector, pretty much. There's a reason for that. It tends to be the superior material of choice, right? If I'm talking, carrier bags, I look at a paper bag versus a plastic bag. The paper bag is 30, 40 times higher carbon emissions. But the consumer doesn't think that. They think, oh, it's paper, it's natural, it's environmentally friendly. The only issue with plastics is at end of life. So when I say reduce, I mean you should still use plastic for the application, but if you can get away with using less material, you should, right? If you can transition into mono, you should. So yeah, that was just a caveat I wanted to say.
Yeah, I think that's a really important caveat, that we can't just shift the environmental impacts we currently have from plastics to another material, because when you shift everything to paper, what happens to the land? The land that we need to grow the paper on. I guess another issue with plastics that is probably a whole value chain is the microplastics as well. It tends to be an issue. So no matter where in the value chain, if we're using plastics, you get that abrasion, you get those microplastics, which we haven't really figured out how to prevent or stop leaking into the environment yet, or how to remove them from the environment.
So microplastics are a really controversial one, because there are some people out there who will tell you it's not a problem at all, right? But there is some emerging research that it shows it is a problem. There are some links to carcinogenic and reproductive health issues, and if I'm taking polyethylene and I put it in the environment, it takes forever to degrade, but it will degrade, and it degrades into these fragments that aren't soluble, so they're there. And then you think about photosynthesizing algae and plankton and stuff like that. It's eating these microplastics. How many people have watched David Attenborough, and we've seen ocean animals and they die and their gut is full of plastics. It's crazy, and it will bioaccumulate up the food chain, and it will affect us as well. But it is a controversial topic, because some of the earlier research around microplastics, they've shown this level of microplastic causes this negative effect, but the level that they've used in their methodology is far above what our actual exposure will be. Right. So this is where there's a bit of controversy, because then a plastic lobbyist will be like, oh no, it's fine, this paper's not real, all research isn't real. But it's like, no, there's caveats. And like I said, there's new research coming out that says this is a problem. We need to address this before it's too late.
What really scares me about microplastics is we're continuously emitting them into the environment, and we don't have any solutions. Once they're in the environment, how do we get rid of it? How do we get it out of our bodies? Like, we don't know. We don't really know the effects fully yet. And that's quite scary to me. In an ideal world, it would be, okay, let's find some solutions to it, or try limit the amount of plastics we use to at least reduce those emissions. But yeah, that's quite scary to me. I feel like every day there's a new report saying microplastics found in the brain, found in the placenta, found on Mount Everest.
Yeah, it's pretty bad. What scares me the most around this topic is a potential infertility crisis that's coming from microplastic pollution, and it's not the only factor. There's other pollutants as well, but microplastics on their own aren't that bad, because most plastics are inert. But the problem is they act as carriers for other pollutants, heavy metals, pesticides, etc. So when they bioaccumulate in your body and animals' bodies, it's not necessarily the microplastic itself, it's all the nasty pollutants attached to that will then cause the negative effect.
Interesting.
Yeah,
you know that actually. So it's like almost like a host. It's obviously a biological organism, but it's almost like a host for other pollutants into your body.
Yeah. And in terms of, you asked how do we clean the environment, you can't. Once it's out there, it's out there. It's very difficult to remove microplastics, and there's nanoplastics. As those microplastics get smaller and smaller, they become nano-sized, and they're even more penetrative into like your cellular structure, because they're smaller. It's easier to get in there, and it's crazy. It's in the air we breathe, in the water we drink, in the food we eat. It's unavoidable at this point, and the only way to sort of combat this is to address the plastic pollution problem. right? So it's to do more mechanical recycling, more chemical recycling. Yeah, it's a bit doom and gloom.
Yeah. Yeah, but there are solutions. Maybe not to the microplastics, but solutions to the amount of plastics we produce and consume. Does mechanical recycling release more microplastics just through the mechanics of grinding up the polymers? And do a lot of mechanical recycling facilities have, I don't know, some sort of mitigation for that?
So yeah, during the process, they will produce microplastics, right? But you don't necessarily, like, if you didn't release it in your wastewater, it doesn't escape the system. So if you were a thoughtful recycling plant, you would capture all of your waste material and you would deal with that. You wouldn't just put it out there. Whether or not people actually do that, I don't necessarily think they do. But it's sort of one of those things that we have to take this one battle at a time. And I don't really, because the problem is, if you say, oh yeah, mechanical recycling, chemical recycling also produces microplastics, it might then give people ammunition to say, oh, so we shouldn't even recycle. But that's not the case. We need to implement that now, and then we can address these issues and improve it along the way.
Okay, definitely. So I guess what I'm hearing from this is there are certain issues with the different recycling processes, but if the recycling facility has strong, robust processes in place to mitigate potential waste emissions, as they should do anyway, you know, we have processes for these pretty long-standing environmental management processes, that can be abated, but often it's used as a kind of like gotcha, right?
Yeah, exactly.
Like, recycling is bad because it emits this, but you know, landfill is bad, incineration is bad. We know that.
Exactly. Yeah.
Okay, thank you. So I've a couple more questions. How do you respond to criticism that chemical recycling may be used as I suppose, almost like a cop-out to reduce the efforts to use problematic and hard to recycle plastics? So we know there's some pretty problematic, hard to recycle plastics, which currently the best practice tends to be you should really try to eliminate them.
Yeah.
How do you respond to that criticism that some companies are using chemical recycling to still continue to produce those?
It's a tricky one because, you know, my personal opinion, as I've already mentioned during this, is we do need to reduce those difficult plastics. We do need to transition to monostructures instead of multi-layered structures. So if the industry is using chemical recycling as a cop-out, then, you know, that's a problem. But I think it depends on who you're speaking to. You know, not every company is like that. Some people are really trying to make a difference, and they understand that it's not a silver bullet. It's part of the whole process, you know. So yeah, how do I respond to the criticism? I would respond to say that when used correctly, this is the solution. This is the way forward, right? When used correctly with everything else that we've discussed. If someone is ignoring that, then yeah, that's a problem.
Yeah. Okay. Yeah. Interesting. And I guess another thing that just came into my head about chemical recycling, I presume it's a really important method for healthcare and pharma to increase their recycled content, because that's contaminated, right? So you wouldn't be able to mechanically recycle waste from hospitals, but if it gets purified through that chemical recycling process, that's a way that they can increase their recycled content.
Yeah, you said it exactly right. So this is one of the advantages of chemical recycling, because how do you deal with this waste that, you know, is contaminated, that you can't mechanically recycle? You're right. Without chemical recycling, your only option is to incinerate or landfill. But if you do chemically recycle it, you end up making you know, your virgin product again, and you do create this circular economy. So this is really where it's useful for your difficult to handle materials. That doesn't mean we shouldn't redesign the system. We should, but even when we redesign the system to make simpler materials, we're still going to have degraded materials that we don't know what to do with. So chemical recycling will always have its place.
Yeah, for sure. And then my last question to you is, so you work for AquaPak Polymers. So I just wanted to touch a bit on how is AquaPak Polymers supporting this transition to the circular economy?
Yeah. So here at AquaPak, we manufacture a polymer called polyvinyl alcohol, which is a water-soluble polymer. Most consumers would see this polymer on like dishwasher tablets. That little bit of film on the dishwasher tablet, that's it's like polyvinyl alcohol. So it dissolves in water, biodegrades, doesn't leave behind microplastics. So how are we helping the circular economy? I would say, if I give an example of one of our applications, so we do extrusion coating, which is coating onto paper or cardboard, etc. If you look in the marketplace and you find coated paper or cardboard, it's typically polyethylene or polypropylene coated onto this paper. When they then recycle that, they don't get very good fiber recovery. So that paper, they can't actually recycle it very well because the polyethylene is stuck to the paper, right? So they grind it up, they put it through some hot water, and it's difficult to fully recycle it, right? Whereas what we're doing over here, we'd make a structure which is paper, our polymer, and then one of the polyolefins on top. And when that's then recycled in the same recycling facility, our polymer will dissolve in water, which then separates the polypropylene or polyethylene from the paper, allowing for a higher and purer recovery of both materials. So in that way, it's enabling a circular economy. But we also have other applications such as non-wovens. So we can make wet wipes, sanitary towels, those kind of products. And you don't necessarily want to reuse those materials. So by making it out of our material, when you're finished, it dissolves in water, it goes away, leaves behind no nasty residues. So in that sense, it's still linear. So I guess it depends on the application. But even then, when it dissolves in water, you can, in theory, collect that water and recover the polymer back from it. So yeah, that's what I would say.
Interesting. So you said that it doesn't leave behind any microplastics. So once it dissolves, what's left? Like what's in that water?
Yeah. So it's a good question, because when I tell people this, the first question I get is, "Oh, can I drink it once it's dissolved?" Right? So let's say I dissolve some in the water, right? The polymer has solubilized. It's still there. So if I was to evaporate that water, you will end up with a powder, which is our polymer. So in that way, you can then reuse it, and it would be circular. But our selling point is, once it's in the water over time, it biodegrades. So bacteria will digest the polymer and break it into smaller and smaller pieces, eventually producing carbon dioxide and water. So once it dissolves in the water, it's still there, but over time it slowly digests and becomes nothing, right? So it's not the perfect solution, but when we look at our current situation, I put some polypropylene in the water, it stays there as a solid piece, right? Maybe over 100 years or so, fragments, and then you get microplastics and whatnot, and they're still going to remain there. It's very difficult for bacteria to break that down. It's not biodegradable. So yeah.
Okay, interesting. So yeah, it evaporates, dissolves into organic matter, carbon dioxide, water, no microplastics, which, as was talked about, is a massive, massive problem. Well, thanks so much for your time, Fabio. This has been a really interesting conversation, digging into all things chemical recycling. I definitely learned a lot. I think Circular Digest subscribers will too.
Hopefully I didn't bore them, but yeah, thanks for having me.
Of course, thank you. See you. Bye.
See ya.